Yay!
Our book decides, which to be honest, I respect them for, and I think it's kind of interesting, hence why I wanted you to read the entire section. They don't start by defining all these new antiderivatives or Riemann sums or necessarily going into all the math of exactly what's going on when you find areas under the curve. Instead, they start with a question that people a long time ago were trying to answer. And what was the question that people a long time ago were trying to answer, specifically in, I think, is it 1600s? Nope, 14th century, even earlier. For Galileo was in the 1600s. What was the question they were trying to answer?
Area under the curve.
No.
Total change.
Yes. Total change. They talked about, they had already figured out how to think through instantaneous rates and the rate at an instant. That had kind of been in the works for quite a while. But once they figured out instantaneous rates, and they were like, well, hey, there are these objects that are moving at variable rates. Give me an example. What's something that would move at a variable rate?
A car.
A car. Unless it's on cruise control, and even then, well, it's not really constant.
A roller coaster.
A roller coaster would be varying rates, right? Sometimes it's fast, sometimes it's slow. What else?
A ball bouncing.
Yes.
Yeah, in some senses, because it has to stop every time it bounces, right? Or every time it changes direction, I should say. That's a better way of putting it. So maybe a better question is, what are things that move at constant rates?
Light.
Time, maybe, in the sense of, light, yeah.
Would light move in seconds squared? 1 second per second? Or just speed?
Well,
It would
light
just-
speed is going to be a velocity, though, right?
but time itself would move. You wouldn't have a velocity.
I said constant rates. I didn't exactly say how to measure rates.
Okay.
So time is moving
Right.
constantly.
Second per second.
Technically, I guess it's saying. So, if constant rates aren't very practical, then question, how practical is the formula distance equals rate times time?
Not very.
Not very.
I guess you can use it in related rates.
You could use average.
Or
If the rate's constant.
No, I'm thinking distance formula.
If you have an average speed or average.
Yeah, if you're talking about average, right? But it's not going to actually model the exact total change. So then the question came up, well, if we have all these objects moving at varying rates, and if we finally figured out how to figure out what those varying rates are, what the rate of change is at all these different times, can we possibly use that to figure out the total change that is occurring in said quantity, whatever it might be?
Apparently, we can.
Apparently, yeah, but it all came back to, well, let's think about, and that's what the guy, Nicole, how do you say his last name? I have no idea. Oresme?
Can I see?
You saw last name, didn't you?
I told you, I read it really fast.
Oresme.
Let me get there.
Oresme? What nationality? Didn't even say, did it say an actual thing?
Probably dying or blind.
Well, I looks Riemann looks Jewish. Sorry, we talking about ethnicity, so my mind made that jump.
No, I understand. I'm not sure what ethnicity.
Oresme.
That's what I was thinking. Oresme? Instead of Oresme? Oresme? Anyway. He basically was the first one to kind of think about, hey, there might be a graphical representation of this. Because we do have the distance equals rate times time sort of formula now. We do have the distance equals rate times time. But how does that correspond to a graph? Where did this whole area under the curve thing even come from, and why does it work? That's the approach that our book starts integration with, which I thought was pretty cool. So how does area under the curve correspond to distance equals rate times time? Well, we start with an easy example, one that we do know, one with a constant, aka steady rate.
I get it.
Yeah, that's what last time was. Yeah. But I'm glad you get it. Isn't it cool? It's really cool.
Dr. Shamel explained this.
Oh.
Can I say it?
Okay, let's keep going.
Hold on, I'll let you get there. But we have a constant rate, right? We have a steady rate. We have a constant rate of 7.5 nautical miles per hour. If we graph, we can show that steady rate. We can show that constant rate, right? But what else can we show on the x-axis?
Time.
The passage of time. So we have from 7 a.m. to 9 a.m., which on the x-axis, this distance, these 2 hours represent the 2 hours that this movement is happening, right? So when we're thinking distance equals rate times time, we're like, yeah, no big deal. Distance, how far did it go, equals how fast was it going, 7.5, times how many hours was it traveling for? No big deal, right? 14, 15, blah, 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 blah. But what does that mean in terms of the graph?
It's the area.
It's the area.
That's what I was
We have the passage of time. We have the passage of time between 7 and 9. We have that distance of 2. And then we have the constant rate being shown by the constant height of 7.5. And so distance equals rate times time is perfectly encapsulated by the actual area under the curve. So that begs the question, what are we going to do then if or when the rates are varying? But before we get to that, what would you do with this one then?
365 times 3.
Yeah, no big deal, right?
Right.
Because graphically, what would we have?
A straight line.
On the line. Yeah. And specifically, we were talking about the rate. What rate are we talking about?
3 cubic yards.
Cubic yards. So I did a dV/dt, right? So the area of volume. But still, a long story short, we would have, in a sense, kind of the velocity.
Is this kind of doing dv dt times dt? That would just give you dv.
Not.
Is this kind of what we're doing?
No, that generalizes a little too much.
Okay. So the indentation kind of just goes out the window here.
It doesn't go out the window, but I think I want to wait until you get to integration to show it. So then when we have our rate and when we have our time, it's no big deal because then we can say, oh, hey, the time, passage of time can be shown in the 0 to whatever, 365. And then we can show the rate of our 3 cubic yards per day. And since it's constant, that's going to be a constant height. And the passage of time, all this accumulation, in the sense of every single day having the exact same rate, all this accumulation can be found. Ooh, accumulation, good calculus term. Pretend he's over there. Can be found just by a simple area, right? So then no big deal. We have the change, and the change would end up being 3 cubic yards per day times 365 days, which works out nicely with units as well. So you just put that. And then we end up with a final answer. Mental math, come on.
15 plus.
Guys. Cubic yards.
The mental math.
I'm sorry, I didn't I do it out loud because otherwise it
We
may
double
just
check me,
distract.
am I right?
Okay.
Okay. So, then the question is then, what happens if our rates are varying? Another way of saying it, a better way of saying it, is variable rates. So constant rates, no big deal, alright, fine. Distance equals rate times time. To memorize a simple little formula, it's no big deal. Why? Because it's a simple area. Or maybe we can say, the area is simple. Why? Because it's distance equals rate times time. Who came first? Well,
The chicken got me it first.
exactly.
I was saying this for the joke.
Oh, I'm sorry.
It's okay though, because technically that is the answer you can always say, because people are always like, I don't know. But if you're talking about individual situations, how do you really know what the person had first, chickens or eggs? I don't know. Depends on whether you're a big scope kind of person or a small scope person.
Oh, I hate this question.
So what's different about this illustration? Variable rates.
Cat.
You know, velocity equals what? A constant? No. Velocity is now varying because it's time squared, so depending on the time, the velocity is going to be different. And not just different, but increasing. And not just increasing, but increasing at a curve, or with a curve. So what was a simple problem, distance equals rate times time, has now become a bit more complicated because how do you do distance equals rate times time without any error? What rate do you choose? There are infinitely many between 0 and 3, right? So we can't just use one rate, so that doesn't work. Okay, fine, let's use the area thing. The area thing is better, right? Okay, well that makes it a little bit simpler in the sense of, okay, we can do the accumulation, we can think of all the different rates at all the different times with area, but then even the area thing gets difficult because now all of a sudden is it a regular geometric figure? No.
Misty,
And so it's a lot of area under the curve. Sure.
couldn't you take a bunch of these rectangles and then cut off top and do geometry and do like area of like a.
You mean like trapezoids?
No, like area of like a. What are those things called? Sectors, and then add that to the
The
area.
sectors, you have to know the actual radius of the circle that forms that curve. And that's going to be super hard. You know what I mean? Because you'd have to have a circle at the base of the area of the sector formula.
I guess.
Which is going to be helpful for polar, but we're not there yet. George.
This one on the right showing is just showing except
Midpoint. Yeah. It's basically showing midpoint. And what has it actually sectioned? It's zoomed in. It's zoomed in on one section of the curve. The long story short, on the left is like, hey, can we make like a triangle and be like, yay, you know what, there's an error, but no big deal. Yeah, but how can we make it better than that? They went ahead and sectioned it into, I don't remember, was it 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. They sectioned it into 12 different rectangles. And if it was 12 different rectangles, what would my base be if they were equidistant?
1/4.
Yeah, because 3 divided by 12. So 3 divided by 12, each of the bases would be 1/4 for the 12 different rectangles that we're fitting in. Each of the subintervals, I should say, would be 1/4. Okay, they're showing 1/4. And they're showing the 1/4 approximately where, oh, they're missing one. There would be one here as well, right? Because then I'd have my 0.25. And right here it would hit, and then I'd have a rectangle. So ideally, they should have shown me more. But either way, I know, those terms.
Wait, say it again?
So if we take this region, this subinterval of 3, this distance, and if we go ahead and section it because we're trying to get less error than if we were to just to do a triangle per se. Wait, what did I say?
You said, we heard you see Trump.
Yeah, I thought you said those trumps instead of those schmucks.
Chump.
Oh.
Chumps. I was like,
That's why I
Have you
said
ever
it
heard that
again.
one?
I heard chumps, but I got suddenly trumps.
social media, our brains.
Right?
I can't use Trump anymore. I can't use chumps anymore. Throw them all out the window.
You can use Peyton Manning.
So the question is, will there still be error?
Yes.
Of course.
Yes. But will there be as much?
No.
How are we going to eliminate that error? We're going to fit in more and more and more rectangles. So before we get to them fitting in more and more and infinitely many, hence getting infinitesimally close, hence finding the limit, hence finding the actual area, we're going to do sums.
Could you find that error using differentials like we did last chapter?
We did approximate
each
area
one.
differentials.
You have to do each one, wouldn't you? And that's just paying the problem.
You could set up a formula that would work its way through and find each one. But it would be approximated. And there actually is a problem in section 1 that does talk about this area. That's not a mean thing, that's an actual understanding. Okay,
That's so funny.
come back. So then question. Where's the particle of 3?
9.
We could work through this problem. Let's work through your books so we give you another one. Go. Particle starts at x equals 0 and moves along the x-axis with a variable velocity. V equals t squared plus 1 for time greater than or equal to 0. Where is the particle at t equals 5? What? I need the total distance traveled. And I'm hoping there's not some backward forward or else I might have some issues because I don't just need the total distance traveled. I actually need the displacement. I need where it is now. But if you think about this curve, my physics people, aka my calculus AB people, aka everybody in here, do I need to worry about it going backwards?
No.
Why not?
Because it isn't going anywhere.
Because of the function they gave us.
Because the velocity is strictly positive. If the velocity is strictly positive, it's strictly moving in one direction. We can show that because the area is strictly positive as well, right? Now it says approximate the area under the curve using 5 rectangles of equal width and heights. Oh wait, I should not have stopped there. 5 rectangles of equal width and heights determined by the midpoints of the intervals. Ooh, that was close.
Oh, man. I don't want to do that.
How do you
It's okay, we got this.
do equal
I know that's why I did.
Oh.
Equal width and heights determined by the midpoints of. Right?
They gotta use some
See?
punctuation.
See, I said that wrong. But there's no need for it. No, it's trouble. Okay. I would have said heights determined by the midpoints of the intervals and equal width, because that would have been smarter.
Those schmucks.
See, I can edit a textbook, I just don't want to write a textbook. That was also what I did. Not literally, but I was thinking about it back in the day. I took a senior editing class as a sophomore and just said, they were weird. and superficial. 1, 2, 3, 4, 5.
So we're going from 0 to 5.
In so many
Using 5 rectangles.
Real quick.
But, question, am I going to go up to the curve at 1 and hit? No, because my sectioning of 5 made 1, 2, 3, 4, 5 rectangles, right? But in that rectangle, where do I want to hit?
Oh,
At the midpoint. So instead of hitting at 5, where am I going to hit?
1,
Or sorry, instead of hitting at 1, at 0.5 instead of hitting at 2. Now they look like they're actually hitting. I'm going in between. So I could show the pictures, but why not let's just show it with math, yeah?
Yeah.
So I can go ahead and if I was to do it my introductory way, I would say, hey, we have 5 rectangles. We would go ahead and say base times height for each, right? What are the bases of each since I made them equal widths? Between 0 and 5. They're all going by 1s, yeah? How do I use heights? Remember, height is where I go up and hit the function f of x. So they're going to be f of x values,
V of
but at the midpoints.
V of each point. V of 0.5, V of 1.5, V of 2.
Exactly.
Sorry.
By v of, we're plugging and chugging, right?
Mm,
But we don't have
To
to.
simplify matters, we could go ahead and just throw in the 1.
Yeah, that's okay. I know I brought it.
And then 0.5 squared plus 1. Would that just be 1/4 plus 1, which would be 5/4? Plus, plugging in 1.5, that would be 3 halves. 3 halves squared is 9/4. 9/4 plus 4/4 is 13/4. 2.5 squared, that's 5 halves squared, that's 25 fourths. 25 fourths plus 1 is 29 fourths. I wonder if there's a pattern. Plus,
yeah. Multiply the top by 2 and add 3.
multiply the top by 2 and add 3.
5 times 2, 10, 13 times 2 is 26 plus 3 is 29.
So let's check it with the next one. So if I was to go ahead and plug in 3/5 or 3.5, that'd be 7 halves, which would be 49 fourths. 49 fourths plus would be
61?
50 what?
61? 29 times 2 is 58 plus 3 is.
Your pattern broke down because I got 53 fourths. Right? 7 halves squared, 49 fourths. 49 fourths plus 4 is 53 fourths.
What's 7 halves? 3.5?
Mhm.
3.5 squared plus 1.
Or do the plus 1. Oh yeah, do the plus 1. I was thinking of the
3 fourths. Yep, pattern broke down.
Snake. This one's plus 8 fourths. This one's plus 16 fourths. This one's plus 24 fourths. 8, 16, 24. I'm not sure how that's working.
Wait, what's 29 minus 13?
But 8 fourths would be 2, 16 fourths would be 4, 24 fourths would be 6.
Maybe there just is
Wait,
no
what
pattern.
was that? 8 fourths is 2, 16 fourths is 4, 24 fourths is 6.
Oh, it's exponential.
No, it's my pattern. Plus 2 plus 4 plus 7.
Oh, plus 2 plus 4? What?
Plus 2 plus 4 plus 6. It's just the pattern of the series. Oh, it's a series! Hey, that's CalcBC. Anyway, coming back.
Good thing they have formulas for those.
Yeah, we're getting there. Hold on. So the last one would end up being plus 2 plus 4 plus 6 plus 8. 8 would be 32. 32 would be 85. And we can see if that ends up working because 85, let's see, we have 9
185.
halves, which would be 81 fourths. 81 fourths plus 4 is 85 fourths. Haha, I found a pattern.
You're fast enough on a calculator.
The answer is 185 for
185 fourths?
or 46.25.
Question. What kind of approximation is it?
Raven?
The midpoint.
Over,
Oh, it's
under,
it's a
or equal?
It's an over.
Why?
You go up and then up to the left, so we have a little chunk. No, it don't make it.
So it's
Never
under?
mind. Oh, it's over.
I don't know, Misty. I
We go up and then we go out to the left and we have a chunk, right?
Take midpoint.
We go out to
Under, because the next thing in the graph, it goes up above it. Because the graph is positive, right?
But see, we have a little bit of over error and we have a little bit of under error. So which one wins?
Because it's concave.
I got you. Let me find out for you.
I don't know.
We do the integral.
I would do the integral and check.
Or we can go to graph. So
My guess would be an over because that's concave up. So there's more over than there is under concave down. Not concave down, but the area above a concave up will be a little bit more than the area below a concave.
46.666.
So we're under.
Yeah.
Under. How come? If we had a more accurate picture, we would see that even though this one does look more because of the concavity, it's shifted a little bit more this way, so we have an area on top.
What do you mean?
Struggle, man.
I think it's too wide.
Hmm?
Is that what you're saying? The graph is too wide?
My section isn't perfect. So then this would be a little bit moved down because the midpoint doesn't necessarily mean the average. So it's not perfectly in between in the sense that these wouldn't be comparable. So this, even though it looks like it's a little bit more, he's a little bit less because he's moved a little bit more this direction.
So because, I get it, because the values more to the right are higher, there's more of the area.
Kind of. Anyway, did we find the approximation? Yes, but question, couldn't this whole process have been summarized in a sum?
Yes.
How would we have done that?
We have to find the pattern. One, it would be 1 times the sum of, I guess you start at 1, or you start at 0.
And we want to plug into our velocity function, that's for sure, right? How do we get 0.5, 1.5, 2.5, 3.5, 4.5?
I plus 0.5.
No, because we did one.
Because it would be 0, 1, no.
They give us 5 rectangles, and we have to divide that by how much we have. So 5 over 1, this is 1. And then, since it's midpoint, we go in the half. So I equals 0.5 plus 1, or plus n.
Oh, you're using n?
Does that work or not?
Wouldn't the 1 come out in front of him?
Dash 2.
No, in front of the sigma.
Why couldn't we do n plus 0.5?
Because if it starts at 1,
If it starts at 1.
oh, because then it would be like, it'd be 0.5, 1, 1.5, 2,
Do we have to go to 5 this week?
But there are 5 encapsulated in 0,
Okay,
4,
yeah.
0, 1, 2, 3, 4.
Mhm.
How do you count? There we go. Wouldn't that generate?
Yeah, but it'd be going 0.5, no, it'd be going 0.51, 1.52, 2.5. No, it'd be including 2.
No, it wouldn't. Because 1.
0 plus 0.5, 1 plus 0.5. I'm not doing multiples of 0.5, that wouldn't have worked.
Oh my bad.
Now question, what if I want to fit in more rectangles than 5 of them?
Just make the top number higher. Go to like 5 or something.
Oh, but what's the dilemma if I make the top number higher? Aren't I talking about a bigger area?
Yeah.
I'm not making it any more accurate.
Oh, you want more?
So did my sum actually, is this showing how many rectangles? No.
Just do it there.
It's just showing the numbers within. So if I started going 5 and 6 and 7 in this formula, I would just keep on moving this way. I wouldn't make that one any more accurate. How could we put this in the summation where we're showing the sectioning? Couldn't we do 5 minus 0 all over n?
5 over n, and n would equal, if n equals 1, it would be 5. We have to start at 0, wouldn't we?
How many rectangles are we trying to do?
5. Don't we have to start at 0? Because they want everything in between 0 as well.
So maybe it's not over n. What if we instead had it go to a? And we divide by a. Can we do that?
Oh,
So then if we have 5 rectangles, we're cutting it in fifths. If we have 10 rectangles, we're cutting it in tenths, etc. We could do something like that. And then we could say v of, How do we get the sectioning, the sub-intervals split into what we need to be split into?
It's the 5 minus 0, but we're doing 5 rectangles. We're not cutting into. Oh, we are cutting into ones, but with midpoint. My bad.
Does that make sense? So now I have to deal with the midpoint though. So I have to take each sub-interval and we have to go ahead and split it in half or find the average of the two. Ooh, the average of the two. How do we do that?
V of, no, not V.
You need each sub-interval cut in half, right? And add the two. How do we get the two endpoints?
N minus 8
I guess it'd be
If we have 5 rectangles.
n plus 1 minus n.
No. That should be n.
plus 1 minus 1. That wouldn't just be a 1.
That would just be 1 actually. This is hard.
Mm-hmm. Don't we move by whatever the distance is, however wide they are?
Yep.
So couldn't we possibly, for each and every rectangle, if 1 is supposed to stand for the first subinterval, 2 is for the second, 3 is for the third, then I can say, okay, start at your left endpoint, which for us would be 0. And then we add however many 5 minus 0s over n, or no, sorry, over a, all times n.
Let's try that.
So we're starting at 0, we're adding, we're going however many lengths of the subintervals we need to, and then we're taking the average. So if we were to plug in 1, when we're starting at 0, we're going over 1, 5 over a. So going over 1, which in this case would be 5. So going over 1, 1, and then cutting it in half. And then for 2, then we're starting at 0, and we're going over 2, 5 over a's, which would be 2. And we're taking the average of 2, which, the average of 2 doesn't work, does it? So maybe we have to change this just a little bit and we have to say, okay, hold on. 0 plus 5. No, 5 minus 0. All over a times n minus 1 plus 5 minus 0 all over a times n all over 2. Aha! And that'll average whatever we need. Now, long story short, is this a bit complex? Yes. Why am I showing this to you? Only when we can put this in a sigma notation, only when we can denote the actual sum itself, can we then say, hey, if a is 5, a is 10, a is 100, a is 1,000, the limit is a goes to infinity, and we can solve the integral by the definition. Which we never did much. And we might see it, but we're not going to see it today. But at least we got an intro to it, and at least we figured out it's kind of hard to write this in like a generalized way where we could change the number of rectangles.
I remember I was doing it. I did it in pre-cal.
Yeah.
It was a big hassle because like
We had to use those formulas, yeah.
yeah, and at the end it was
Yeah.
like
Did it work?
Yeah, it's supposed to equal 185 over 4, right? Not the actual?
Right.
Okay, that works.
Right. But then now here's the cool thing. What did George just do? He threw this Riemann sum into his calculator. So what could you do if you needed to do something in the book where it says, now I didn't give you any of those, but where it says, like, use the calculator program to now go to 10 and 20 and 100 and 1,000.
Learn the Riemann sum.
Just change your top bound. So you say, oh, let's make it 100, 100, 100, 100. Let's make it 1,000, 1,000, 1,000, 1,000. And what are you going to be approaching? The actual.
Yeah, 46 point, or 46 and 2/3.
Yeah, the integral from 0 to 5 of t squared plus 1, which helps us find the actual area. Now, kiddos, we're not going to go through the entire exploration, but real quick, the first two examples they showed, when they say RAM, what are they talking about?
random access memory.
Rectangle.
Rectangle approximation, is it method?
Yeah.
Something like that. Basically, it's using rectangles to approximate, and LRAM was from the left, MRAM was from the midpoint, and then RRAM was from the right. They're basically saying, we will next section. They're basically saying each of these, hey, is the left always lower, the right always upper, and the midpoint always whatever in between?
No.
It's all based on the increasing, decreasing, concave up, concave down nature of the function. So all of this would have you go to the sine function that's messy in and of itself and be like, hey, is it always the way that you think it is from the first two examples? And the answer is no, it's based on other factors. Whew.
This drives me up.
Whoa! In the very first section of integration, they introduced disks.
Oh no.
Washers. At least they didn't do that.
So,
Yeah,
what
that's
are you talking about?
Question. What
Can't
are
you-
we supposed to do?
Estimate the volume of a solid hemisphere of a radius of 4.
Just do the first one and multiply by 2.
Take this disk and multiply by 2 and that gets all the rest?
No, get just the top half.
Oh, okay. I see what you're saying.
Oh, like cut them in half and then multiply by 2. But you still have to do each of the different disks, right?
Yeah, you don't have to do it however many times.
You're just getting a long. All you're saying is get a longer.
You're saying do the longer ones and do the shorter ones in times 2. Yours actually takes a little longer. The question. So how are we thinking about what we were doing this entire section, how we were taking a problem that we don't know how to do and doing it with rectangles? How do we use those rectangles to then go ahead and be a part of a disk, aka a cylinder? Okay. Well, kiddos, hold on. Question. If this is a 3-dimensional disk or a 3-dimensional, really skinny, I should say short cylinder, it's kind of wide actually. What's the formula for volume of the cylinder?
Wait, this is this.
R squared H.
R squared H.
Oh, cylinder.
Yeah, it's 3-dimensional. So this is the sphere.
Yeah.
So then question, how do we plug into this for, how many do we have? We're going to have to generalize this, right? Let's just do like a dot, 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 and then we'll put it in a nice formula and not have to worry about it. So question, how do we find the volume of the first disk? We're hitting where?
R is 4. Oh, well, the
Dx.
We're hitting where? But when x is equal to 0, right?
Yeah.
Okay. But we end up with pi times, what's my radius?
4.
That is true. It's going to be the height at 0, which is 4. Squared, and what's my height?
No, 16. No, 8. 8. No? Because.
1/2. 4k.
Because the
because
dx is
It's from 0 to 1, 2, 3, 4. And it's happening.
4 has been cut into 8, so the height of this one is going to be only 1/2. You got to think about the cylinder. His radius is 4, and then it goes all the way around to get here, but his height is just 1. It's just a little tiny one.
Wait. It's 1?
Yeah.
It's not from 4 to negative 4?
Because this is our cylinder.
Oh.
Yeah.
This is our radius, and this is our height. And our height is, sorry, not 1. Our height is 1/2.
Oh, the height is the distance between.
Exactly. So then, what is our height for all of them? What's our height?
And pi is always going to be.
And the pi's are always going to be there. Those are constant. So what are going to be my radii for the next one? Well, what's the next one?
1/2.
Ah, it's at 1/2, and I have to plug in 1/2. Aw, stink. So it's going to be the square root of 1/2 squared is 1/4, and then 64 fourths. 64 fourths minus 1/4, 63 fourths. Ew. Square root of 63 over 2. Anyway. Squared. Look at that.
Ew.
So
And then we're going to keep going. So how do we generate this one?
63 over 4?
Yeah, square root of 63 over 4, and I just square rooted 4 over 2. So that was cheap, just a little bit. We can keep going, right? So then we could go ahead and say the volume with 8, sectioning into 8, they said S said 8, whatever, is equal to, we can pull out the 1/2, we can pull out the pi, and all we have to figure out is,
The sum.
yeah, the little in-between pieces. The little in-between pieces, we're plugging into what function? Square root of 16 minus x squared. So I can say function at 0, which is 4. Function, I need squared though, right? Function at 0 squared plus function at 1/2 squared plus function at 1 squared plus, I'm going to keep on going until I hit where? Where's my last one?
No.
I'm not using 4. What am I using for my last one? 3.5. Hey, if you were allowed to use your calculator, which you definitely are, question, how can you simplify this without even having to make an even sum, first of all?
Just do it for the definition.
Without having to do a summation.
Y 1 of.
Yeah, you can go ahead and throw your function square root of 16 minus x squared into your y equals, and then do y of, and then make sure you're squaring each of the y of values, and then throw it in one line. It's not going to be hard, right? But what are we doing? We're accumulating. With error, yes, and specifically, obviously, what kind of error?
Over.
It's going to be an overestimate of the volume, right?
How do you determine that? Just without looking at the.
Without looking, you have to think about the concave nature of the curve and how it's concave down. And so if we're coming from the left of the concave down, the left will always jut out and have an over approximation. Or you can think, if you're coming from the left, you're assuming the height is going to be constant, but the height is decreasing. So hence, you're going to have an overestimate.
I get that, but what if it was in the middle?
If it was on the right, you have to do the
It'd be
same
under.
thing in the sense that from the right, you're assuming it's the lowest height, but as you move to the left,
You see you're under, because it's concave down. So if you go to the left, it'll be higher. So then, what if it's the middle?
and the midpoint, you would have to actually look at your subinterval and cut it in half and see where it hits. So like in this one, if we were to cut it in half, that'd be at 2, right? And this is a good illustration, thank you for asking that, Jargo, because if I was to do a midpoint, what do you guys think it would?
Over.
Over, because there's more space. See, even though the 2 is the midpoint here, it's not the midpoint of the line. So you have to think about, okay, where would it hit in the function values, and that will give you your clue as to whether it's under or over.
I'm not like as in if each rectangle is.
No, I know, sorry, I'm doing one representative to show you the idea of what's happening on each side.
Is it because?
Like the left, I could do one big left one, see the over. I can do one big right one, oh, that's 0. That's under. But I can do one big midpoint for the entire subinterval, and it kind of shows you the trend that's going to happen as you section the small sections.
And it's because.
Because with the function is having the exact same concave down, decreasing nature the entire time. So what we can see mimicked in one big one is what's going to be truly happening at each of the smaller.
So you can't really do it without a graph.
Without knowing the characteristics of it. Yes, you might be like, oh, yay, we didn't finish. But, actually, we kind of did. So, yay. Homework's already updated on chapter 6. If you want to call them Riemann sums and you're doing them in your mind, you may. The nice thing is it starts off with just distance equals rate times time, but then it starts to get a little more interesting. Just a hint. Do you ever Oh, just a hint. If you have a linear radius, it's geometric in its area too. Correct? I don't know.
That's
It might be.
on Twitter.
It might be.